Okay, here I'm going to go over the homework. So I guess I can just show you once 38 is already done. We did that in class. Came up with the domain and range as well. So that is done. And we're going to go to 39 and continue from there. Just focus this. There we go. So the diameter of a tree grows according to the function here, where d is the diameter and t is the time in years. So just go by, write the letters here. This is your x and this is your y. So we, in this case, have time in years followed by diameter in centimeters, right? So make sure you understand which variable is which. Make a graph of the diameter as a function of time. So I will first enter this into my calculator. Bunch of stuff going on there. Natural log of x. I know that this is increasing, and I know, right, you should know the general shape. If it's increasing, we're expecting something to this extent, right? That's the behavior that we're expecting. So let's go ahead and graph it. Oh, I should probably change my window. I'm going to go window zoom 6 standard, and then just increase that a little bit. Just so I see more, and there you go. That's pretty good. Okay, so there you see the graph, and I'm going to pick a few points that are important for this graph, and one of them I know already is 5.13. Okay, this is straight from the equation, so these are reference points, and maybe I will do a couple more. Second trace 5. Second trace 1. X is equal to, and here are the following. So I'm going to maybe go with 10, x is equal to 10, and then maybe x is equal to 30, something like that, and figure out the y values for that. So second trace 1, x is equal to 10, that's 14.20. Second trace 1, let's try 30, that's 18.53. And I think we're pretty good there. So this is on the side here. So I technically have 1, 2, 3 points, right? I'm going to grab my ruler and go ahead and graph this. So A. And of course, time positive, and the diameter should be positive as well, right? So time in years and diameter in centimeters. Done. And let's come up with a good scale here. So I'm going to go to 50, maybe 10, 20, 30, 40, 50, 60. That's pretty good. And then here I know it goes to 18 here, but I will probably go higher. So 10, 20, 30, 40, 50, because we're not told at all some kind of domain and range or some kind of just graph to here. So you just make sure you graph it so that you can tell what that graph would look like, where the points would go, and so forth. Right? So 10, 20, 30, 40, 50. And so here we go. For 5.3, that'd be right here. This would get me right about there to 5 something, right? This actually does have an x-intercept. So we could essentially find that as well. Might have to zoom in a bit. 0.27. 0.270 is the x-intercept. We want y2 is equal to 0 second trace right, for that. So we actually have it right here. It's not quite touching the y-axis, okay? And then we have 10. At 10, we are at 14, something like that. And at 30, we are at 18. So it should go higher. So we have this going on here. Still increasing, but slowly, right? So we have d is equal to 5.13 plus 3.94 natural log of t, okay? So that's the graph done. B, determine the diameter of the tree after 15 years. And notice diameter would be the y value, right? So y2 is equal to, sorry, my bad. They're asking for the diameter after 15 years, right? So time is my x values. I apologize for that. Second trace 1, x is equal to 15. And I make sure that, right, my time is in years, not anything else, right? Hours or whatever. So second trace 1, 15. That's 15.80. Y is equal to 15.80 centimeters. Okay, that's the diameter of the trunk. C, determine the amount of time required for the diameter to reach 20. So that's, right, my Y value. We have a pretty good idea, but second trace 5. So see, if you monitor the growth of trees or even people, right, there's a bit of a faster change and then it kind of plateaus and it slows down, right? So that's where logarithmics are very useful. So y2 is equal to 20, and there it is, right? I think this will work. That's 43.56. 43.56. 43.56 years. Okay. Explain the meaning of the x-intercept. I'm just going to check here. Was it a negative? It can't be because it would never cross. Okay. So what's the meaning of the x-intercept? Well, when the diameter is 0, right? Basically, if you compare the points 0 for the diameter, the time is 0.27, right? So what's up with that? Well, at the very beginning, when you plant the tree, right, it's a seed. So until it germinates and comes out of the ground, and for you to actually start seeing at the beginning of the tree or trunk, some time has elapsed, right? So that's why we don't start quite at 0 in this case. It represents the time in years, right, of 0.27 years that elapsed before the tree was even visible. Okay, there was a point where, right, if times 0, you'd be looking at if this is the soil, right, the seed is down here, so some time goes by until it actually goes past the surface and is visible, right? So that's why some time has passed, 0.27 years. We could figure that out in days, right? About 98, 99 days has gone by for a tree to be visible, right? So that's what it is in this context. So my domain, in a sense here, let's make sure we understand that. technically the domain starts right there. So the domain would start at 0.27 for time. And in this case, there is no indication that the tree will completely stop growing. So we just go like that, infinity. And the range, we go all the way from 0, right? 0 all the way to infinity as well, because there's no limit to what the diameter could be, and there's therefore no limit for how long that would take, okay? Because there's no indication that saying, for example, that the tree would stop growing, right? The diameter stops at, like, let's say 45 centimeters, in which case we would stop right here, right? So our domain would be restricted also on the upper level, on the upper ends, okay? Let's keep going. So it should take you less than 10 minutes to answer, right? This video is about 11 for this first question there. The amount of time required for investment to grow to a stated amount is given by the equation as follows, right? Where t is the number of years, watch, right? T is your y variable here, and a is the target value in dollars to be reached. So technically, this is the target in dollars, and this will be time in years. Okay, so very important to, with logarithmic in particular, be careful there. Remember, this is your y and this is your x, right? If all else fails, remember that. The initial amount of money to be invested is 12,500. Make a graph of the time required as a function of the amount of money for the amounts from 10,000 to 100,000. Okay. So what do we know here? Right off the bat, we know that this is an increasing function. So for logarithmics, right, it would come here and just keep growing this way. And we know that the initial amount of money is 12,500. So that means that the initial amount is 12,500 at time 0, okay? So normally we put time here, and you understand, I've been telling you that many, many times, right? But this is the point that you're given. So your graph, right, will be 12,500, 0, according to this, okay? And so we want to make a graph that starts at 10,000 all the way to 100,000, because remember, the x-axis right now is your dollar amount. So we'll go ahead and do that. So don't let things like that throw you off too much. Maybe just go by what you know, right? You know which variable goes where, your x and your y. Type it into your calculator, start graphing, start putting some points down, and then maybe the rest will follow and just fall into place, okay? So here we go. Clear. Plus 0.38. And this is log, so you've got to be careful. I will keep that y2 is equal to 0 in there, and I think this is where we know. let's analyze this a bit more. We know that there's a point on this graph which is negative 259.65, right? So we know it's gonna do this. So this point is actually in the negatives down here, and then goes, and we also know that it's gonna go through this point because of the question, right? So we need to adjust our window. I'm gonna go my x max, since we're supposed to go all the way up to 100,000, I'm gonna go 110,000. And my y max, that represents time, I'm just going to go 100 for now. We'll see. And there's your graph. Okay, so you adjust as needed. And remember, dollar amount needs to be positive, so obviously you would stay here, and you know that a logarithmic it never crosses the y-axis, and time has to be positive, so we would be in quadrant 1 again. So A, let's make that graph. That's the target value in dollars. This is your time in years. And so we will go ahead and graph this. Let's go ahead and find our x-intercept, second trace 5, because sometimes it isn't quite, it is almost 12,500, almost. Okay, so, but we're going to go with this. That was, I guess, just a help, right? But it's almost 12,500, it's 12,494. So the x-intercept would be y2 is equal to 0, second trace 5. And so it's 12,494.48, 0. And if the amount is 100,000, so we're going to come up with a couple here. This is a must, right? I'm going to go second trace 1, x is equal to, I'm going to go maybe in the 50,000s, x is equal to 50,000, come up with a y. Then I'm going to go x is equal to 100,000 because it does ask for it specifically, so that would be a good idea to include that. So second trace 1, 50,000, and that gets us to 38.17. Second trace 1, try 100,000, that is 57.25, right? And so now we have more points, so that will help us. I need to go all the way to 100,000, so I'm going to go 10, 20, 30, 40, 50, 60, 70, 80, 90, and I'm in trouble. That's okay. We'll make it work. 100,000, we'll put that here. 20,000, 40,000. Oops, that's a bit too much. 40,000, 60,000, 80,000, and 100,000. Okay, and then so time in years, we go all the way to 57. So let's go to 60, 10, 20, 30, 40, 50, 60. There we go. Okay, so 12,494. And this would be 10, 12, 494 is right about there. And then at 50,000 here, I'm at 38, which is close to 40. And at 100,000, I'm at 57. It's closer to 60, right? So there's your and this is t is equal to negative 259.65 plus 65.38 log of A. There's your graph. Perfect. Next, B. Determine how long it would take to reach 25,000. Oh, you gotta be careful. See, I'm doing the same thing, but I catch myself. Why? Because I wrote this down. Okay? So we're given a dollar amount, so it's actually the x value. 25,000. That's 19.09 years. And C, determine how long it would take to reach 50,000. We already did that right here, but that's just coincidence. but it helps. Okay. Uh, D, determine how much money you could have in 25 years, and that is actually a Y value. Y2 is equal to 25. Let's see if we need to. No, we're good with the window. Trace 5, enter, enter, enter. That's 30,985.92. Just remember $sign. Okay, put units down and then you're good. And domain range never hurt. It never hurts. So we'll go for the lowest domain, the lowest X value according to this model is 12,494, all the way to, in this case, it does seem to give an indication. I would be very clear about that on a test or quiz. And then the range would be from time 0 all the way to however long it takes you to get to 100,000. And we already have that, which is 57.25. Okay. There you have it. Next. I think I will just do a couple more here. Radioactive isotopes, carbon dating. I think I'm going to do this one here. Modeling data involving logarithmic patterns. Sorry, I'm going to pause this here once. Yeah, I'm going to keep going. If you can always fast forward or just stop watching, right? Okay, here. Logarithmic. In this case, this is A and this is B. And B is negative. So this is actually going to be decreasing. Okay, because B is less than 0, which is negative. I know a point on there is 1A, 199, sorry, 0.316. And we're talking with an initial percentage of 100%. All right, the following equation can be used to determine the length of time to reach a target percent remaining. Make a graph using your calculator. We're going to go ahead and do that. I'm going to first type this in, right? So it's really 199.316 minus 43.2809 natural log of x. I'm going to leave that in there. I'm going to find my x-intercept. So my window is probably way off because, right, one of the points is 199, right? Like, so I'm guessing it's not going to be too far. Let me just think here. Length of time based on the initial. So it doesn't say if it's in years, right? Or anything. So we're just going to say T is for time and P is for the percentage remaining. So percent remaining, and this is going to be time in years. We're just going to assume that, right? Didn't say anything. So the x-intercept, we're going to find that. That's definitely important. I feel like my window is overkill, so I'm going to try 100 for x max. And this y max would be probably a good idea. let's go 110 as well. And x max, because it's percent remaining, should be 110 as well. So my x-intercept will be further down here on the x-axis, right? Graph it, and there it is. It's right there. So second trace 5. It's really good. If it's decreasing, it's good to find it and then kind of work backwards, right? So we have the x-intercept, which is y2 is equal to 0, second trace 5. It's still a lot easier than doing this by hand, let me tell you. That's 100, 0. No surprises. As the question was saying, it's true, right? There's 100% remaining at time 0. In this case, it jives, right? Some questions haven't been jiving. So then we're going to go more points, second trace 1, x is equal to, I'm going to let x equal to like 50%. That gets you to 30.00. Nice. For the y, right? If x is equal to, let's say, 25, that's exactly 60. Not bad at all. Y is equal to 60, sorry. So there you have your reference points. Then you graph it. And here you have percent remaining. Just to make sure, this is time and years. Here we go, and so 100, so 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Boom. And then 50. Here I need to go, it says at 25, I'm at 60. So maybe I will try, let's look at my window here. I'm going to increase my X max to like 200. So see, I went all the way to 200, and that's when it starts getting really close. So I'm just going to do that same thing. So 20, 40, 60, 80, 100, 120, 40, 60, 80. So 180, that should be pretty good. So 20, 40, 60, 80, and so forth. Oops, sorry. 20, 40, 60, 80, 100, 120. We're going up by 40 here, right? So this would be 160. All right, so that's a point, and then at 50%, we would be at 30, so this is 30 right there. At 25, we're at 60, that's exactly on there. And maybe one more, I'm just going to use my calculator for that. At, let's say, 10, that's 99, almost 100. 10, we're at almost 100, so this would be 100 right there. And then 1, at 1, we're at 199, right? I actually didn't fit that on there, but this would be good enough. You can fast forward this video, right? Or watch it at a faster speed. This is too slow. It's all good. B, how long would it take for there to be 50% remaining? We already did that. Second trace 1, x is equal to 50, and that's just 30 years. Y is equal to 30 years. C, how much would it take, how long would it take to figure out 25% or 6.25 second trace 1, x equals 6.25. That is 120 exactly. Y is equal to 120 years. D, determine what percentage will be remaining in 2211. So you need to have the number of years, right? So years till then would be 2211 minus 2011. Right? That'd be 200 years. And years is our y variable here, so y2 is equal to 200, and then you go second, trace 5. And you'll find out what x is. So you are probably going to need to increase your y max to, I'm going to go to 10, y is 200, there it is, second trace 5. So it would be 0.98. 0.98% remaining. All right, and then for E, state the domain and range for the function given the context. So I guess we're going to assume that at this point it's safe, right? It's so far down the road. So for E, we would go domain. It's our percent remaining, right? We'll never really get to 0 probably. So 0.98 to 100. And the range would be all the way from 0 for time 0, right? 0 all the way to 200 in this case. And obviously the question would have to say it's considered safe at that point, right? For us to come up with this domain and range. Let's make that assuming 0.98% is safe, right? Or something like that. We're assuming that that is safe. Okay, next. There's an exponential coming, right? Carbon dating uses carbon-14 to determine the age of an organic item. Carbon is continually replenished in the atmosphere, but once a living thing dies, then the carbon decays from the amount at the time of death. The equation modeling the C14 remaining, starting from 300 milligrams of C14 is here, where A is the amount remaining in milligrams and T is the time elapsed in thousands of years. Very careful there. So time in thousands, right? And amount remaining in milligrams. So every point refers to that. So graph this using your graphing calculator. Let's type that in. Actually, what do we know? This is A and this is B, right? B is less than, or B is between 0 and 1, therefore decreasing. Okay. So we are going to have ourselves, if we don't consider the word problem, right, it's going to be decreasing from left to right. And we know there's a point 0A is on there. So 0,300 is our reference point, right? So there's a lot of things that you know without even graphing it. So we go ahead and type that in. To the power of x. So my window, when it comes to the y, I should be at least up in the 400, so 350, let's say. Let's try that. There we go. And And let's figure out a few more points. I'm going to try, based on my window right now, the highest X value displayed is 110. That's way over here. So this would be 55-ish. So let's try 10. Second trace 1, X is equal to 10. We have 89. So I'm going to go, there's no X-intercept here. So second trace 1, X is equal to, let's make X equal to 10, Y is equal to 89.49. Second trace 1, let's make it 20. Let's try that. X is equal to 20. We have 26.69. Right, so I think that's good enough for our reference. So we go ahead and graph it. So this is time in thousands of years. Got to watch out there. Of years, thousands of years. And this is amount remaining in milligrams, right? And so we can, if you want to see how far, right, we can go second trace 1 and go 100 or 80 or something like that. That gets us very close already, right? When we're at 80, we're at 0.0. That's a bit too close. So I think if we graph to like 50, we'll be fine. So 10, 20, 30, 40, 50. I'll do a 60 yet here. And then we'll go all the way up to 300 here, right? So 50, 100, 150, 200, 250, 300, 250. So 100, 200, 300. We are on that. And 10 gets us to 89. 20 gets us to 26. That's a pretty good idea that that's going to work. So we go down through that, through this, and then ever so slightly continue inching our way towards the x-axis, but never really reaching it. So 300, and that's 0.88606 T. Okay, good enough. Then we have the B, find out how much carbon is remaining after 5,000 years. So remember, time is X in this case. So second trace 1, X is equal to 5,000. But remember, what you're entering, this is in thousands of years, right? So this is 20 times 1,000, so that's 20,000 years, 40,000 years, 60,000. So if you want to know what it is for 5,000, you actually need to, if it says in thousands, you need to divide this by 1,000. And for us, it represents X equals to 5 on this particular graph, okay? So we're going to go second trace 1, X equal to 5. So after 5,000 years, it's 163. Let me see here. Y is equal to 163.85 milligrams. Okay. C, what's the half-life of C14? The half-life. So you're just going to take what you started with, which is 300, and just split it in 2, right, to get 150. And then you're going to figure out how long that takes by finding the intersection. So we're going to go Y2 equals 150, graph it, second trace 5, and it's 5.73. Watch what I'm going to do here. X is equal to 5.72988 and so forth. thousands of years, right? So when you get this statement, you can say thousands of years. But if you want to just say years, right, you just take, I'm going to keep that separate, right? X would be 5.27 something times 1,000. So now you can state it in years. So I'm going to go 5.72988 times 1,000. That's 5,729.88 years, if you want to write it like that, okay? So you choose, depending on what the question asks for, right? How long will it take for only 5 milligrams to be left? So y2 is equal to 5, second, trace 5, right? y2 is equal to 5. $33.84, right? So I'm going to say 33.84 times 1,000. And I'm going to use all the decimals, sorry. 3845779. Right? And that is 33,845.78 years. You can also just shift the decimal over 3 spots, right? Because 1,000 has 3 zeros, and then away you go. What is the domain and range of this function in this context? I would have to say that they're not, this question isn't being very specific, right? When would you consider the carbon to be basically gone, right? Is it the 5 milligrams that we just did? So based on, if we do base it on that, domain is my time, right? We go from time 0 all the way to 33,845.78. For the range, we would then go all the way down to 5 milligrams, and we start with 300. Okay, that's assuming that D is the limit, right? If we assume that, then that's what it would be. And again, I promise you that on a test or whatever, I'll be very, very specific. If there is no indication whatsoever, right, then we would go for a range. We would go 0, not including. It'd be 0 with a round bracket all the way to 300, including the bracket, right? So you never quite touch 0, but you go 300 from 0 to 300. If you wanted a domain and there was no range there, or no limit whatsoever, you'd go 0, including all the way to infinity, actually, right? So look at the context. I feel like we just did this. Yeah, we did this. So this is a repeat. Never mind. Yeah, and this is an investment question. It's the same as, very similar to before, except for time as in months. So you got to watch out. Yeah, I bet you they will. Yeah, it's going to be years, 20 years. So you will be tempted to type in 20 for years, but it's really needs to be converted to months. So you just go by that. 45, and it's basically all copy 45 to 48. So don't worry about those. Yeah. So the rest, I think I'm going to stop here, and I think you have enough material to get you going at this point. If you have any questions, just let me know.